Hello, students. Today we want to continue our discussion with functions and talk about some of the properties of functions. I also want to include some ideas about more function algebra so that, again, we will continue to practice and get better and better as we make our way to the calculus sequence. Again, properties of functions can still be studied without the calculus, but there will be certain things that will require the use of limits and derivatives that will not be available to us unless we are looking at it more intuitively, like you saw in the last lecture, where we looked at the difference quotient and let the h pass to 0. So I will always talk about these ideas to get you prepared for the calculus sequence. So first, one of the very important ideas that we study about calculus is the increasing and decreasing aspects of functions. And what we want to do today as we start out is actually define what it means for a function to increase or decrease. So let me share my screen. Now, again, like I said before, when we consider the idea of increasing function or decreasing function, what comes to mind is values of the function getting larger or increasing if we call the function increasing, and then values of the function getting smaller or decreasing if we call the function f decreasing. Now, it certainly would be convenient if we consider the entire domain of the function and the function just does one thing throughout its domain. And that's usually not always the case. For instance, I've given you two examples that are very unique, but give you at least a good idea of good examples of these two types of functions. So let's look at that. Now, what I've written here is just a very simple way of describing algebraically what it means for a function to increase. And notice I'm not establishing any interval or anything. I'm just saying f is increasing if and only if the value of x1 is less than x2. And of course, we tacitly assume that these are in the domain. Otherwise, this wouldn't make sense. So we think of elements in the domain where x1 is less than x2. If the function is increasing, then the value of the function should increase. That is, f of x1 should be less than f of x2. Or if you want to say it, if x2 is greater than x1, f of x2 is greater than f of x1. So as you move through the domain of the function, the values of the function get larger or they increase. So that's a formal definition. Now, if we think of decreasing, we're going to think of the values getting smaller. So if x1 is less than x2, we would expect in this particular case that the values actually get smaller as we proceed. That is, the value at x1 will be bigger than the value at x2. Now, the first time you see this, that appears to be correct, but it's better to look at two simple functions that have these properties. Let's look at the square root function. I've used this function in our analysis in the first few lectures, especially when we were talking about inequalities and absolute value. The square root function is a good example of an increasing function. We have used that in our calculations. And so if you take an x1 less than x2, of course, the domain, let me go ahead and write that down. The domain of f, at least the largest domain, would be 0 to infinity. That is, we can take square roots of positive numbers and 0. And so if we take x1 to be less than x2, we would expect that the value of the function would increase at x2. And just looking at a very simple graph of the square root function as we understand it to be, that intuitively makes sense to us. So what's interesting about the square root function is that we know as we increase the size of the input, the output's going to get larger. You know, if you take the square root of 1, you take the square root of 10, clearly the square root of 10 will be bigger just by definition of the square root. So again, that's not a rigorous proof, but it certainly supports our intuition about taking square roots. And what's interesting is that when we do get to calculus, we will be able to provide a mechanism for determining whether or not a function increases or decreases. So that's something we have to look forward to. Now, let's look at another function, g of x, domain of g. Well, we don't want to divide by 0, 1 over x, so we just have to omit 0. So when we look at this particular function, it has the properties of the decreasing function, and we see that it decreases throughout, but what we notice is the existence of a vertical asymptote. I mentioned that in the last lecture, and we'll say more about this as we continue our studies. But what happens is that when we see that we have a 0 in the denominator, division by 0 has no sense to us. There is no definition for that. And so what's happening as x approaches 0 from the right, the function becomes larger and larger and is unbounded. The closer you get to 0 from the right, without actually getting to 0, the function values can be made arbitrarily large. Now, from the negative approach, what happens is that our function values get infinitesimally small. That is, they diverge to negative infinity. So what we have is this really interesting situation where the function diverges to negative infinity as x approaches 0 from the left, and it diverges to positive infinity as x approaches 0 from the right. But whatever the case, as we consider values in the domain, that is x1 less than x2, as we simply intuitively think about reciprocating a number, the values get smaller. So if we think of x1 as being 1 and x2 as being 10, and we reciprocate those, clearly 1 over 1 is bigger than 1 over 10. Again, that's not the most rigorous proof of that, but it certainly supports our intuition about why the sketch of the graph has this shape. And so we can look at the graph and see that the values are rising and that the graph values support that. Here we see that the values of the function are getting smaller, and we see that the graph sketch here supports that. So just remember, a graph is not perfection. It is simply a reasonable sketch of what we think the function is in a visual sense. We don't always need a graph, but a graph is a visual aid that can often help us when we are actually trying to work with certain parameters in a problem. But just remember, the understanding of the function is what allows us to come up with a graph. Now, what I want to do is say a little bit, before we talk about some more of the properties of the function, I want to go ahead and say a little bit about the algebra. The algebra of functions is very important. And when we look at algebra of functions, we think about what we did with the difference quotient, and we want to apply this in a more general way. So let's talk about adding, subtracting, multiplying, and dividing functions, at least in a formal way. So number one, we'll say f plus g of x. That would be a sum. And so if we just assume that f and g are functions and we say f plus g, that means the sum of the functions applied to some what? Value or number in the domain of both f and g. So again, if we are evaluating a sum of two functions at some input, the input must make sense in f and the input must make sense in g. So we would define this formally as f of x plus g of x in a pointwise fashion. That is, we would apply f to x And we would also apply g to x and then add those two values. So this is a pointwise definition, and it would have to be the case if we're dealing with functions. It would have to be defined this way. And then, of course, as I said before, x would be in the domain of both functions, domain of f. And of course, we use the intersection symbol, domain of g. This is important to know because as we continue in our work, we will come back and use these. Just like when we were doing the difference quotient, we had to take the difference of two functions. And so we're assuming that x and x plus h are both in the domains of the function. That is, that makes sense. And of course, our calculations would be of no use to us if we weren't assuming the existence of these particular real numbers being in the domain of the function. So 2 will be the difference. And of course, this won't be anything difficult. Instead of adding the functions, we will subtract them. So you're thinking I probably could have done a twofer with this with a plus minus, but I'm going to do it separately. So again, the function f minus g would mean that we would apply f to x and we would apply g to x, but then we would take the difference of those two values. And then, of course, x must be in the domain of both. Remember, when we say x is in the domain of f and in the domain of g, we use the intersection symbol. We have to. And now we have two more operations. So we're looking at the addition and difference of functions as being very much like arithmetic of real numbers. However, we must now include the portion that illustrates where the input must be. So that's the additional information that we need to list when we talk about adding or subtracting functions. Now, when we think of multiplication, we just juxtapose the f and the g, just place them beside each other. You can put a little dot there, but it's not required. I think, again, juxtaposing two letters does assume that we will have multiplication. Now, again, we apply f to x and we apply g to x, and we take the product of those two numbers. So again, pointwise, and I'm sounding like a broken record, x must be in the domain of both functions. Not a surprise. And then for the last one, we're going to think about the quotient. So we'll just say f divided by g applied to x. And I'm sure you're already thinking this. This will just mean a pointwise evaluation for each function, and we take the quotient. So we say f of x divided by g of x. And we have one additional restriction. We know that x must be in the domain of f and in the domain of g. But clearly, g of x cannot be 0. Now, you're thinking when we write all of this to the side, it's not really necessary. I mean, but it is necessary. It's like, what do we want? Well, we must assume this. For instance, if we take the sum of two functions or the difference of two functions, we assume that it's well defined. And so when we write x in the domain of f and domain of g, we really know that. In the back of our minds, it's there. But this is simply a reminder. And then, of course, we remind ourselves that division by 0 is not defined. And so this, again, would be a restriction that we would impose. So these extra items here are not really required in a formal definition, but they are important that we apply this as we do the work. So we include these, especially as we work through a college algebra class, to make sure that everyone is thinking about the values must make sense in both functions. So for instance, if you had, let's just take a simple example here. Say we had f of x equals the square root of x, and we had g of x equals just a very simple polynomial, 2x plus 3. Now, of course, the idea here is that when we consider the two domains, one is all real numbers, because of course it would not make any difference as to what input we use for g, because this is simply a first degree polynomial in x. But now, of course, with the square root function, as we saw as a good example of an increasing function, x must be non-negative. So here we have domain of f will be all non-negative reals. And of course, domain of g is all reals, because of course there's no restriction here on this function unless we just make it that way. Now, of course, when we take the intersection of the two, that's just going to give us the non-negative. So now when we add the square root of x to 2x plus 3, we are assuming that the values of x are non-negative, because that would mean that the x would make sense here as well as here. So this is what I'm talking about when we start to add functions. We have to consider the fact that the values of x must work in both functions, not just in one. So here's an example of what we're talking about here. So again, and as you do things pointwise. So for instance, we might say the following. Say if we had f times g of 2. Okay, well, we just apply the definition. First, we know that 2 is in the domain of both functions, so this makes sense. So this would be f of 2 times g of 2. That is our definition here. We have a specific value of x, or we could just write the formula. Either way is fine. And so we need f of 2, which will be the square root of 2. And then we need g of 2, which is 2 times 2 plus 3. So this is the square root of 2, and then we have 4 plus 3, which is 7. So we get 7 times the square root of 2. So what's interesting about the definition is that it's not a surprise. And you might be thinking, do we need the algebra of functions? Well, we definitely do, because as I've said before, the calculus is basically a treatise on differentiable, continuous, Riemann integrable functions. And so when we apply the calculus to the functions, we must apply algebra, just like we have here. For instance, we would want to know if the limit as x approaches c of f and g both exist, would that allow us to compute the limit of the product function? And the answer is yes. But we would need to understand the pointwise definition of the product to be able to prove that and to work with that successfully in the calculus. So again, the algebra of functions, though right now seems a little bit, pedantic in the sense that, well, okay, we know this. When are we going to have heavy use of it? Well, not until you get to the calculus. But it will be important that as you work through problems, that you respect the new restrictions of the domain, just like we have here. And of course, if we had an input here that was negative, then we would just simply say undefined, because we have this requirement due to the square root function. So the algebra of functions is just a way of treating the functions arithmetically. Okay, we add real numbers, we subtract real numbers, we multiply real numbers, and we divide them. And as we think of functions as being machines that output real valued functions of a real variable that output real numbers, then we should be able to manipulate those numbers algebraically, as we have written here. So we call this the algebra of functions. So if you want, just say algebra of functions. Now there's going to be another algebra that we're going to talk about, which is called composition. And that'll be another way to combine functions that will be of great use to us. And we will do that soon enough. Okay. Now, I want to give you another property having to do with the concept of even and odd function. Now, again, when we study the trigonometric functions, we will find an even greater use of even and odd. But before we get to those, we need to know what they are. And they're not difficult, but the definitions are fairly restrictive. So if you just come up with a function, there's a pretty good chance that it will not be even, nor will it be odd. But we will study functions, especially the 6 basic trig functions, which we will find possess either even or odd as definition. So we need to know about these. So number one, well, I'll just do Roman numeral 1. F is an odd function. And sometimes we just say, if we're just short on words, we'll just say f of x, or f is odd, and we know what we mean, if and only if. Number 1, x element of the domain. We always have to have a symmetric domain if and only if the additive inverse is element of the domain of f. Now, of course, the important part here is that this doesn't mean that the domain doesn't have any discontinuities, or doesn't omit particular numbers. It just means that if we have x, we must have its additive inverse. So the domain must be symmetric relative to 0. So if 3 is in the domain, you must have -3. If 1/2 is in the domain, you must have -1/2. So you have symmetry about the 0. Okay, that's what we need. We need a symmetric domain. So this just basically says symmetric domain. Without that, you don't have even or odd, and you just stop. And that's the same for both even and odd functions. So that'll be repetitious. And then there's an algebraic quality. That is, how does f attack the additive inverse of an input element? Well, it absorbs it. So even functions are very mysterious. That is, the additive inverse, the negative, absorbs. So what does this do for us in terms of a picture of the function or a graph? This gives us y-axis symmetry. Y-axis symmetry. So if you think of the y-axis as a mirror, the graph would be the same on either side of the mirror. Like you think of the standard quadratic function, y = x squared. That's an even function. And that's very easy to show that it is even. And so what I would like to say is that as we work through things and we think of very simple examples that we can remember to apply to certain definitions, that will help us when we get to more complicated functions. And so to the side here, just as the simple example that I gave, I'll just say f of x equals x squared. Now, why is this very simple? Well, the domain is all real numbers, which is clearly symmetric relative to 0. You get the x and the additive inverse for free. So we have domain of f is all reals. And of course, we're not making a restriction here, so that's a check. And then, of course, f of the additive inverse of x is the additive inverse of x squared. And of course, if you want, that will just absorb, but you can just think of this as a -1 times a -1 and an x squared. So again, the negative x is just -1 times x and a -1 times an x. Of course, the x times the x is the x squared, and the two negatives here absorb because of our properties of real numbers. So this is indeed f of x. The idea here is that we know that the additive inverse times the additive inverse is no additive inverse. The negatives absorb. So by the laws of exponents, we get the x squared. This gives us the 1, and we're good. So if you want to just say 1 times x squared, just kind of beating it to death. And now, of course, 1 times the x squared one being the multiplicative identity, we get x squared. So indeed, for the x squared function, not only do we get the symmetric domain, but we get the algebraic restriction that's required. And that's exactly why when we draw a picture of the quadratic, it has the characteristic shape that gives us the y-axis symmetry, just like this. So when we think, ladies and gentlemen, as y-axis symmetry, we think of the y-axis as being a mirror. And on either side, we just basically get the reflection. So that's what we refer to as y-axis symmetry. So again, you can look at a graph of a function and it may appear to be even, but remember, that's not a proof. To prove that a function is actually even, you must work with the definition. Okay. Now again, as we realize that a particular function has the definition of even, then when we sketch the function, we want to make sure that the y-axis symmetry is apparent. Now, of course, we're not Rembrandt, so it's not going to be beautiful, but it should at least illustrate the fact that there is y-axis symmetry. So remember, with the even function, you need the symmetric domain, and then, of course, the function itself will absorb the additive inverse. And so what you're seeing here is that the negative actually absorbs by using the properties of real numbers, which again is very useful. Number two, and you know, I've been doing even, and you're thinking the whole time, why didn't I put even up here? Excuse me. Let me just I'll go ahead and do that. So we did the even function. I think I wrote odd initially, and then when I wrote this is for the even function. So I'll make that change. So now we'll say f is an odd function if and only if, number one, again, we have the symmetric domain. X is element of the domain of f if and only if the additive inverse of x is in the domain of f. So again, we have a symmetric domain. Yeah, the math never tells us fibs, but we do. So again, just remember here, the absorbing of the negative means the even. So that's even. Now odd has a little change to it, not much. We got the symmetric domain, but now what we find is that the additive inverse survives. That is, f of the additive inverse of x is actually the additive inverse of f of x. Now that is really interesting. We could say it's odd. When we think even function, we think, well, it's even, in the sense that we think of squaring the negative. Squaring the negative absorbs the negative, right? So we can think of the even function as parroting that. The negative goes away, it's absorbed. At least it's now, into the background, so to speak. It's there, but we don't see it. That's why I use the term absorb. I mean, we might need to bring it out because we need to rewrite one as x squared over x squared, or we need to rewrite something in a way that will allow us to move forward using a conjugate method or whatever. The idea is that with the odd function, the negative survives. It simply factors. Now, what does that mean? It means origin symmetry. So you're thinking the polynomials probably give us some of the best examples of even functions. Now, when we get to trig, I'll just write this: g of x equal the cosine of x. That will be a very famous even function. The cosine. Very, very useful function. And you will find that out when you study the trigonometry. Now, one thing about this that's easy. Let's just take a very simple example. Let's just take the cubic function, x cubed. And just like this, it'll be easy to prove. That is, the domain of f is all real numbers. So we get a check there. Now, of course, we would want to show that the negative survives, and that's easy to do. So we have, in this case, negative x cubed. Now, I'll do the same thing I did here. I'll just simply say, well, that's just a negative 1 times x 3 times. So that's a negative 1, a negative 1, negative 1. And of course, you could just do, the negative 1 cubed, but I'm just kind of parroting what I've done here. And then you've got x times x times x, that's x cubed. But of course, the 3 negatives give you a negative. So positive 1 times negative 1, that just gives you negative 1 times the x cubed. And that just gives you the additive inverse of x cubed, which is the additive inverse of the original function. So what's important here is that you work through the calculation. Notice in the even, we have f of negative x is f of x, the negative absorbs. Here we have f of the additive inverse of x, or negative x, gives us the additive inverse of f of x. The negative does not absorb, it survives, so to speak. So we say the negative survives. For the even function, we say the negative absorbs. So this is really important. And even though these are very, very simple examples, they really are good examples to remember. And then, of course, just as a little extra, h of x, when you study trigonometry, the sine function will be a very, very famous example of an odd function. And this is really the backbone of Fourier analysis. Joseph Fourier revolutionized convergence by writing functions as infinite series of sines and cosines. And when the Fourier series came around, then we had excellent and elegant methods to solve partial differential equations. So it was really a revolutionary thing. We have infinite series, but then of course the Fourier series added the additional dimension that revolutionized electricity and magnetism. And basically why we have our technology today, those types of mathematics have been exploited. And we simply, like I say, we're married to the Fourier series, we're married to the calculus because it is the backbone of our technology. And so that we will have these nice examples as we move through STEM mathematics will even make what we do more rich. And the study of trigonometry you will find to be very interesting, and it will utilize all of the terrific mathematics that we're learning now. So remember, when it comes to even and odd, very restrictive. I mean, this is a lot for a function to have to do, okay? And so we don't expect tons and tons of functions that we, happen by to have these restrictive properties, but when they do, they certainly make a great simplification. So now that you know the two major functions of trigonometry possess either even or odd qualities, that will not only affect their arithmetic and their graphs, but it will also have a direct impact on their calculus. So the thing is that these are very rich concepts, and we will study them, maybe not as much in college algebra, but you will certainly continue that in pre-cal and then also into the calculus sequence. So again, learn these ideas. They will be very useful, and use this technique as functions become more complicated. Let me just give you one example, an additional example here for you to test. And then we'll talk about some maxima and minima. Now, for instance, let's look at the following function. Let's call this h of x. Of course, we use the h in the difference quotient. Say we have this function. Let's see here. Let's find an interesting one. So we'll have the absolute value of x divided by the square root of 3 minus x squared. Okay? So what we want to do is determine even, odd, or neither. Okay? So just remember, you check the domain first, see what that is. And then from the domain, you can go to part 2 if you have a symmetric domain. So first, notice that this is just like when we do the difference of two functions, or excuse me, the quotient of two functions. So the absolute value function is a nice function. It's defined for all real numbers. And then, of course, the square root function downstairs is going to be what gives us our domain. So now notice, in this particular case, we'll say the domain of h will be dictated by the denominator. First, let's just make, let me just kind of break this down into a couple of pieces before I do this, just so you don't think I'm just mowing over it. So when we think of this, we can look at this as maybe f of x divided by g of x, thinking about the algebra of functions. And so now the domain of f is just the domain of the absolute value function, which is all real numbers. We can take the absolute value of any number, and we've spent a lot of time with absolute value, kind of a fun function. And then the domain of g will be all x, such that what, 3 minus x squared is what, greater than 0. We can't divide by 0, so we can't have equal to 0. And this is an example that we used in our last lecture that I put on your homework. Again, very simple if you think about using the absolute value. Now, what does this mean? So if and only if, and we can move things around, we can just go ahead and add the x squared to the other side. This will say x squared is less than 3. And that gives us the conjunction if we apply the square root. So applying the square root gives us the absolute value of x, that is the square root of x squared is the absolute value of x, less than the square root of 3. And of course, this is the conjunction. So x would be an element of negative root 3 to root 3. And that is symmetric relative to 0. Now, when we take the intersection of these two, we just get that. So, for instance, the domain of h will now be the intersection of the domain of f and the domain of g, which will just give us negative root 3, or the additive inverse of root 3 to root 3. Okay, so I took an opportunity to dress this as a quotient. That is, the numerator is the absolute value of x. The denominator is the square root of 3 minus x squared. And then, of course, give us some opportunity to deal with some of the algebra of the absolute value that we dealt with in our previous lectures. Again, very, very straightforward, very straightforward. But these types of calculations, again, you can also do this with BVs and factor the difference of squares and get the x minus root 3, x plus root 3. That is certainly a valuable way to do it. But since there's no x term, you can simply look at this as a conjunction. And that's really simple. It's a really simple exercise to think of it like this. But how you choose to navigate that is completely up to you. I think if you have a confidence in one or the other techniques, use that. So now the symmetry we have, so that's a check. And now we want to, so we can think about this as part 1, and then part 2, we just want to see how does H react to the additive inverse. So let's go ahead and do it. Let's apply the definition. So now we have the absolute value of the additive inverse of x, and then we have the square root of 3 minus the additive inverse of x squared. So now we've seen these before, so we don't have to sweat too much. But of course, this is just the negative 1 times x. And we know that the absolute value of the product is the product of absolute values. And then, of course, downstairs, we've already done this calculation. The negative absorbs. So we have 3 minus x squared. Just remember, negative x quantity squared is just negative x times the negative x. That's one way to write it. Maybe a little bit differently, but I'm not skipping steps this time. And then, of course, we have negative 1 times negative 1, x times x, x squared, which is the x squared like we did before. So you don't have to write that down every time. You can just say, well, the negative absorbs, we're good. And then, of course, the product here, so we have negative 1 absolute value times the absolute value of x. And of course, that's just a 1. This part here just equals 1. And 1 times the absolute value of x is just the absolute value of x. So now when we look at this, we're good to go. This is just the original function, h of x. So what we see, and again, these calculations come up over and over. And so you don't have to spend a lot of time going through the details. You maybe can jump from here to here and then use the properties of the absolute value. But what we see is that in this case, the negative absorbs, and by definition, H is even. So remember when I wrote it initially and put odd and this said, oh, this is an even function, that should remind you that when we have the even function, the negative in this case absorbs. With the odd function, it survives. Now another thing that's nice about this is that when you get to the calculus, you will also remember this. And then as you apply derivatives and you apply other machinery to the function, you will know certain aspects about the graph that will make this very doable. So again, remember what's important here is that maybe we don't have all of the picture yet because we don't have the luxury of having the calculus yet. We're preparing for that. We can still keep all of these ideas on reserve and use them when we need to do more complicated work, as we will find in the calculus. So again, this is a nice example of applying the definition of even and odd. So students will say, well, how will I know? Well, once you get the symmetric domain, then you apply this, and what's going to happen? Well, either what? The negative will absorb, the negative will survive, or you will get neither of those. That is, you won't get a clean equation. You won't get the additive inverse of this, or you won't get h of x. So if that is the case, you just say neither. So don't worry about the fact that it doesn't work. If it doesn't work, then you don't have one of the two specialized functions. So that's fine. So that's why the problems will say prove even, odd, or neither. And just remember, most functions will probably fall into the category of neither because these are restrictive definitions. Now, I wanted to say just a little bit about an example from your lecture notes that is of interest. And this is a nice picture here. Now, what is interesting about this is that you think of increasing and decreasing functions, okay? And when you think about that, you think of the graph rising and you think of the graph falling. That is increasing, the graph is rising, decreasing, the graph is falling. So one thing that you noticed about with the original lecture on functions is that when we have the constant function, then the graph for that particular part of the function is a horizontal line. So this is what I was talking about. In general, functions will be a combination of things. You won't just have one particular attribute that flows through the entire function. You may have several different attributes going on at one time. So notice here, from the x value of, again, -5 to the x value of -4, the particular value here, that is the function, is increasing. Now here's what's interesting about this. When you think about these intervals, you think, well, do I include the endpoint or not? Well, that'll be relative to the problem. So usually when we think about a set of increase or decrease, we think about, for instance, the open set. And then we have to think, well, does that allow us to include endpoints or whatever? And it actually does. It actually does. And in the calculus, if you have a function increasing a positive derivative of an open set, you can extend to the endpoints. But what I will suggest here is that you follow the restrictions of the problem. They will either state to give a closed interval or an open interval. And if they say give the open sets, then you don't include the endpoints. And so that's just a restriction that you will see with the problem. And notice here that as you move from the x coordinate -4 to 1, the function is a horizontal line. So we say it is constant. And then, of course, as you move from x coordinate 1 to 4, the graph is falling or decreasing. So what's important here, and I can also add this. And this is important. This is how your answers will be included here. Notice here they are including the endpoints. Okay, so these restrictions are that they include the endpoints, and that's fine because you can always extend to the endpoints. So again, as you read the problem, be sure that you are following the restrictions of the problem. And some textbooks will include endpoints and some will not. So these are inclusive. I just will remind you that when you work with certain calculus texts, authors will say, okay, just give me the open sets. But again, you don't think of increasing over a point, okay? You think of increasing over a set of content, okay? Not just a point. You don't think of an integral of a point. You think of an integral done over a set of content. So if you include the endpoint, it doesn't make it wrong. It doesn't make it right. It just makes it correct. If you want to include or not include, you can't look at one as being more correct than the other. They're both correct. And so, again, that often depends on what the author would like as a statement of answers in their particular text. I apologize that's not a universal thing. I mean, it's like when you define the inverse secant function in pre-cal, some authors will choose a particular definition that makes the inverse secant function increasing. Others will take another definition that doesn't provide that. But some authors will say it makes the derivative computation easier or whatever. So it just really depends on the author and the definition that is chosen. I will say this, that most inverse trig functions are defined universally, and you don't always have to worry about that. So this is actually a visual, and it is not very difficult, but until we get the advent of the calculus, our analysis of functions will not be as elegant and as precise as we want them to be. So to say a little bit more about this, let's look at an example, at a clean sheet of paper here. Let's look at a simple example of here. So, and I'll just draw one. Now, lots of times when we talk about polynomials and things, you can have what we call relative extrema or local extrema. They mean the same thing. And again, textbooks will vary as to how they say that. So let's think of a very simple example here. So we have a polynomial function. Now notice, and I will say that this is what we call peaks and valleys, so to speak. And I'll notice we have a peak here, we have a valley here, and we have a peak here, but the function can extend indefinitely. Now, what's important here is that when we think of this peak here, we think of this as a local maximum because the function will be extending and it can do many different things. And of course, if it's a polynomial, the end behavior will be an infinity or negative infinity if the domain is not restricted. So we can look at this, if you will, as like a C1 and this point as a C2. This we'll say that is the graph of F. And we'll look at this as like a C3. So what we're going to say is the following. We'll say F of C2, or we'll start with C1, is a local maximum of F, meaning that we can take a small interval, a symmetric interval about C, and we could just call this of length delta 1. So the length on either side from C1 to the endpoint here is just delta 1. So again, we'll take delta 1 to just be a positive number. What does it mean, local maximum? This implies f of x is less than or equal to f of C1 for x element of, and we'll write it this way, we'll just say C1 minus delta 1 to C1 plus delta 1. Of course, the way I've drawn it, it would only be equal when the x is equal to C1. So we subtract delta 1 from C1 to get this endpoint, and we add delta 1 to C1 to get this endpoint. And so we say local maximum because this is a local occurrence. We don't necessarily, the book will often say absolute. Normally, if we just say maximum, that just means it is the largest value of the function, period. But sometimes the word absolute is used just to emphasize that point. But local or relative maxima mean that locally, this is the largest value of f. But if you go a little bit farther outside of that interval, that could not be true. But locally, it's true. Now, of course, you might say the same thing for f of C3, but let's do the C2. We'll say f of C2 is a local minimum, local minimum of f. And what that means, we can do the same thing. We'll go a distance delta 2 on either side. Delta 2 is just a name for a value, positive value, delta 2 on either side. And so this will imply that f of x, in this particular case, again, notice this is going to be a minimum, will be greater than or equal to f of C2 for x in the interval C2 minus delta 2, C2 plus delta 2. So again, to get the endpoint here, the left one, you subtract delta 2 from C2, that's the distance there. And to get to the right endpoint, you add delta 2 to C2. So again, what we see is the graph is moving in this direction. So the f of C2 would be a small value, the smallest value locally, the minimum value. So we say local minimum, or sometimes in some textbooks, they say relative minimum. Okay, so the minimum is relative to the interval about the C2. Now, of course, if we look here at the C3, we see we've got another local max. So let's do delta 3. Delta 3. Delta 3. So we'll go ahead and do this again. So now, and if you like, let's just go ahead and plot these points. We have C3, F, C3. We have C2, F, C2. This is good practice for when you do the calculus. And C1, F, C1. Right there. So this implies, or in this case, we'll just say, before I get to the implies, F of C3 is a local maximum. Local maximum of F, which implies, again, F of X is less than or equal to F of C3 for X in the delta 3 neighborhood of C3, for X element of C3 minus delta 3 to C3 plus delta 3. So again, this is an occurrence that is local. Now it seems like this is a whole lot of writing for something that's really simple, but it's important because when you do the calculus, you work locally, okay? And so you've got to do your arithmetic based on symmetric intervals. So if I never talk about these types of intervals, if I never talk about this type of arithmetic with absolute value and symmetry, then when you get the calculus, it's like Greek. It doesn't make any sense. And so I will use Greek letters, and I'll use letters that you will use in the calculus, especially when you get to trig, you'll use a lot of Greek letters. And just because we run out of the standard English alphabet and we need more letters. So again, just think of the fact that now we can see that we have an increasing function here, but then for this interval, we start to decrease. So we can say that definitely, if we want to go ahead and write this in, and then we'll include the endpoints. So we'll say decreasing, and we'll just confine ourselves to this piece right here, C1 to C3. We'll say decreasing C1 to C2, include the endpoints, and then we'll say increasing C2 to C3. The graph is rising. And again, the author likes to include the endpoints here, and that's fine. And then, of course, if you want to add more points as we go out, but we see the graph is falling here, rising here. So that gives us our local maxima and our local minimum. Okay? So again, remember, you get maximum or minimum locally when you have a symmetric interval about some value in the domain, where you can say for the local maximum, this is the largest value in that symmetric interval. Or for the local minimum, this is the smallest value in that symmetric interval. Okay, so it's very simple. None of this is difficult. It's just more writing. Again, but you need to think about the arithmetic, the greater than, the less than, because it really is important. Okay, now there's one more item that we need to discuss, and you're going to think it reminds you a little bit of the difference quotient. And it's called average value of a function. Now, I'll say this, when you think of the secant is the same thing. There's no difference. When we do the difference quotient, we could call it that, but we just don't do it. And so I'm not really sure why there seems to be this distinction when they're basically saying the same thing. But I will say this, by the time you get to calculus, you will know what the slope of the secant line is. You already know. It's just called rise over run. So there is a definition that the book uses that can be useful. So suppose f is a function. Suppose f is a function defined on, we're going to say, a closed bounded set A to B. So just like when we were doing the increasing, decreasing, including the endpoints, okay? So not only does the A and B are in the domain, all the points in between are also in the domain. So we say this set is in the domain of F. Again, we always make that tacit assumption that we have enough points to do some work with the function. We got to live in the domain and work. And when we think about calculus, we have to have enough points in the domain so we can get really close to numbers. The number that we're approaching doesn't necessarily have to be in the domain. It's nice when it is, but it doesn't have to be. We just have to know that we can get as close as we like to that point without dropping off into some abyss or whatever. So we'll say the average value of f on AB. And sometimes we write it like this. We just say, I think there's a, oh yeah, here's what I do. I would do like F average, like that. You're thinking, my goodness, if we have to write the average value of F on AB, can I just kind of shortchange it to that? Yeah, let's do that. And we'll say this equals, and this is going to be the rise over the run. This will be F of B minus F of A divided by B minus A. So this is just like the difference quotient where we did X plus H, X, okay? It's the same thing. We're just replacing the X plus H with B and the X with A. There's no difference. This is rise over run. So you might want to say this is just slope of the secant line. Like I say, I think there are always things or objects that you calculate, but they're no different from what you've already been doing. And you need to understand that. You need to know that even if you change the letters, it doesn't change the arithmetic that you're doing. So even though this sounds complicated, it's just basically the slope of a secant line, which is basically a difference quotient. So if you're asked to find the average value, just like we do the difference quotient, you just substitute the values, take the difference, and then divide by B minus A, and you're done. So this is a very simple way, again, to look at the slope of the secant line. And in your work here, there's a simple example that I want to work. We've got, let's see, here we go. We'll do it. We have f of x equals negative x cubed plus 3x squared, and the interval is -1 to 4. So there's the A is -1 and the B is 4. So this is like really simple, but again, it's the slope of the secant. So let's do it. So we'll say the average value of f will be f of 4 minus f of -1 divided by 4 minus -1. So let's just go ahead and fill it in. And if you note here, we can factor some here, so we don't have to work so hard. So notice here, we have the negative of 4 cubed plus 3 times 4 squared. That's the first part. Minus, so we have the negative of -1 cubed plus 3 times -1 squared. And of course, 4 minus a -1, that's 4 plus 1, which is 5. So just, I think what's good about this is just, keep track of the negatives. They're not difficult, but just keep track of them. So now, if you will, here, we've got a negative and a positive here. So let's just factor the 4 squared. So we have 4 squared, and we have a -4 plus a 3. So again, just factor the 4 squared from each. Remember the negative in the first and then the 3. And then we have minus. Now, of course, we have the -1 cubed, which is -1 made negative, is just a +1. And then, of course, -1 squared is just 1. So that's plus a 3. So just a little bit of algebra with arithmetic divided by 5. So now notice we have 16 times a -1. If you factor, the numbers are easy. And then you have minus a 4 divided by 5. So now you've got a -16 minus a 4 divided by 5. So this is a -20 over 5, which is -4. So what you're seeing, let's see here, where is that? Yeah. So this is number 5. And basically they just give you the value here. So notice that this is very much like the function algebra. And so I can see why the author is interested in defining the average value of a function. Many calculus texts will do the same with the definite integral. But again, it's the slope of the secant line. And again, don't think that this is something that's just been created to be an academic nuisance. It's rephrasing the slope of the secant line in terms of other objects. But notice, we have the difference of functions, okay? So you see this function notation is very, very important. You say f of 4 minus f of -1. So that means you evaluate f at 4 and you evaluate f at -1 and you take the difference. So this is the difference of two functions, okay? So that, again, function algebra. And then the denominator is simple. That's just the difference of two numbers. But notice here, if you factor, the arithmetic is simpler. And so we get the average value of the function on the interval -1 to 4 by definition is -4. So that is just the slope of the secant line. Because if now when you think about it, you think about the point at 4 and you think about the point at -1. You connect the 2 points, but now, of course, it's a negative, so you see the slope is falling. The line has a negative slope, so it has the decreasing deal, which you learned in Algebra 1. So again, just remember as you do these computations, think about what we did with the difference quotient, where again, we were doing the slope of the secant line. It was just phrased differently, okay? So let me make a few points here as you work with these problems. Don't look at them as dry and boring. I mean, in some cases, it just seems like we're making a lot of, hoopla about something that doesn't appear to be that difficult. But the concept of function, I think, is not overly difficult, but you have to respect the algebra of the functions, and you have to respect their domains. And so as you reviewed solving equations in the earlier material and also looking at basic inequalities, we see where all of that algebra and arithmetic is now placed upon the functions. Because as we work with the algebra of functions, we're forced to deal with inequalities and equations. And we're also forced to deal with what? Absolute value. So again, think of the function and the function algebra as just an extension of the algebra that you have been doing. And just remember, the benefits of hard work now will definitely pay off. As you continue to work with equations and inequalities, we will continue that. We will work with functions and their properties, and then expand upon them as much as we can. And then once we've kind of done as much as we can with polynomials and theory of equations, we'll move into logarithmic and exponential functions. So there's lots of good stuff to be learned. And like I say, spend consistent time with each topic, master that topic, and know when you see it again, it'll actually be a lot easier. The thing about calculus is that it requires, like I've said many times, and I will continue to repeat myself, the study of calculus requires a very fundamental understanding of the basic algebra and functional analysis that you have been learning. And on the surface, one kind of problem that you work is very simple. But when you combine many, many different topics that are required for one problem, you must have a flow to your knowledge. You must have a confidence in your knowledge. Otherwise, you'll feel paralyzed and be afraid to move forward. So just make sure as you're doing your work that you make sure that you are continuing to build confidence, okay? Well, I'm done with what we're doing today, and so I will see you next time. Thank you.